Hello students, this is Usha from G.K.Jain High Secondary School. Today we are going to see Electromagnetic Waves Part 1 in 12th Standard Physics. 12th Standard Physics, Electromagnetic Waves Part 1. So in this electromagnetic waves, today we are going to learn about displacement current and Maxwell's equation. So electromagnetic waves. The work of James Clerk Maxwell, who actually enlightened the concept of light from his theoretical prediction, is that light is an electromagnetic wave which moves with the speed equal to 3 into 10 power 8 meter per second. Later his work confirmed that light is just only small portion of electromagnetic spectrum, which ranges from gamma rays to radio waves. So we have learned in the 4th chapter, that is the Faraday's law of electromagnetic induction. The time-varying magnetic field produces an electric field. So Maxwell strongly believed that the nature must possess symmetry, and he had a question when. So later he proved that the Hertz prediction, and then everyone said that it is clear. So in today's digital world, cell phones have a greater influence in our day-to-day life. It is faster and most effective mode of transferring information from one place to another. It works on the basis that light is an electromagnetic wave. In hospital, they were used for X-rays, and also as well as in home, we are using for the microwaves for cooking purpose. The microwave is also an electromagnetic wave. There are plenty of application of electromagnetic waves in engineering, medical, defense, and also in fundamental scientific research. So we learn about the basis of electromagnetic waves are covered. Maxwell correction to Ampere's circuital law. So in Faraday's law of electromagnetic induction, which state that the change in magnetic field produces an electric field. Mathematically, we can show that integral of E dot dl is equal to minus dou divided by dou t of phi b, which is equal to minus dou by dou t of integral over surface b dot ds. In the same way, integral of L over E dot dl is equal to minus dou by dou t of phi b, which is equal to minus dou by dou t of integral over S b dot ds. So, where phi b is the magnetic flux and dou by dou t is the partial derivative with respect to time. So the equation gives the electric field E is induced along a closed loop by a changing magnetic flux phi b in the region enclosed by the loop. Now Maxwell gave another set of equation that is given in the PowerPoint presentation on the right hand side, that is integral of L, closed integral of L b dot dl is equal to minus dou by dou t of phi e, which is equal to minus dou by dou t of integral over surface b dot ds. In the same way, integral over L E dot dl is equal to minus dou phi e divided by dou t, which is equal to minus dou by dt of integral over S b dot ds, where phi b is the electric flux. This is known as Maxwell law of induction, which explains that magnetic field B induced along a closed loop by the changing electric flux phi b in the region encircled by the loop. So, in order to understand this, we have given here one circuit, right? So, let us consider a situation of charging a parallel plate capacitor. The medium in between the capacitor plate is a non-conducting medium. The electric current passing through the wire is the conducting current, which we will take it as IC. Therefore, when a magnetic needle is kept near the wire, deflection is observed, that we learned in our 3rd chapter. In order to compute the strength of magnetic field at a point, we use Ampere's circuital law, which states that the line integral of the magnetic field B around any closed loop is equal to mu naught times the net current I threading through the area enclosed by the loop. The equation is given as integral over L b dot dl is equal to mu naught into I of t, where mu naught is the permeability of free space. Now we can calculate the magnetic field at a point P, which is shown here in the diagram. Draw an Ampere loop which encloses the surface S1. Therefore, using Ampere's circuital law, we get integral over S1 b dot dl is equal to mu naught IC, where IC is the conducting current. Suppose the same loop is enclosed by a balloon-shaped surface S2. So it means that the boundaries of two surfaces S1 and S2 are same, but shape of the enclosing surface are different. As the Ampere law applied for a given closed loop does not depend on shape of the enclosing surface, the integral will give the same answer. Applying your Ampere's circuital law, we get integral over enclosing S2 is equal to integral of B dot dl equal to 0. The right side of equation is 0 because the surface S2 nowhere touches the wire carrying conduction current and no current in between the plates of the capacitor. So the magnetic field at the point P is 0. So Maxwell resolved this inconsistency as follows. So what he did, that is shown in this next diagram. Due to external source, whether it may be a battery or a cell, the capacitor gets charged up because of current flowing through the capacitor. This produces an increasing electric field between the capacitor plates. So there must be a current associated with the changing electric field in between the capacitor plate. So in other words, the time varying electric flux existing between the plates of the capacitor also produces a current known as displacement current. From Gauss law, the electric flux between the plates of the capacitor 5E is equal to the integral of E dot dBA, which is equal to EA, which is equal to Q by epsilon naught, where A is the area of the plate of capacitor. The change in electric flux is d phi E by dt is equal to 1 by epsilon naught into dq divided by dt, which will be equal to dq by dt, which is given as id, which is equal to this epsilon move to the other side. So we'll get epsilon into d phi E by dt, where id is known as displacement current. So displacement current can be defined as the current which comes into play in the region in which the electric field and the electric flux are changing with time. So whenever there is a change in the electric field takes place, displacement current is produced. So Maxwell modified Ampere's law as integral of B dot ds is equal to mu naught I, which is equal to mu naught into IC plus ID. This IC plus ID will take it as I, which means the total current enclosed by the surface is sum of the conduction current and displacement current. When constant current is applied, displacement current ID equal to 0 and hence IC is equal to I. Between the plates, the conduction current IC is equal to 0 and ID is equal to 1. Next we'll go very important question, Maxwell equation in integral form. The first equation is nothing but the Gauss law is let the net electric flux to net electric charge enclosed in a surface. Mathematically, it is expressed as integral of E dot dA is equal to Q enclosed divided by epsilon naught, where E vector is the electric field and Q enclosed is the charge enclosed. This equation is true for both discrete or continuous distribution of charges. The electric field lines start from positive charge and terminated at negative charge. The electric line do not form a continuous closed path. In other words, it means that isolated positive charge or negative charge can exist. The second equation has no name, but this law is similar to Gauss law in electrostatics. So, this law can also be called as Gauss law in magnetism. The surface integral of magnetic field over a closed surface is 0. Mathematically, integral of B dot dA is equal to 0 and no name is given over here, where B vector is the magnetic field. This equation implies that the magnetic lines of force form a continuous closed path. It means no isolated magnetic monopole exists. Third equation is Faraday's law of electromagnetic induction. This law related electric field with the charging magnetic flux, which is mathematically written as integral of E dot dl is equal to minus d by dt of phi b, where E is the electric field. This equation implies that the line integral of the electric field around any closed path is equal to the rate of change of magnetic flux through the closed path bounded by the surface. So, the electric energy supplied to a house from electric board by using Faraday's law of induction. Fourth equation is modified form of Ampere's circuital law. This is also known as Maxwell's law. This law relates the magnetic field around any closed path to the conduction current and displacement current through that path. Integral of B dot dl is equal to mu naught I enclosed plus mu naught epsilon naught d by dt of integral of E dot dA, where B vector is the magnetic field. This equation shows that both the conduction and also the displacement current produce magnetic field. These four equations are known as Maxwell's equation in electrodynamics. This equation ensures that the existence of electromagnetic waves. The entire communication system in the world depends on electromagnetic waves. Hi students, you all have learned about the displacement current and then the Maxwell correction to Ampere's circuital law. Thank you students, we'll meet you in the next video.